Discover how quantum computing is revolutionizing artificial intelligence and machine learning. Quantum computers promise to accelerate artificial intelligence by processing information in fundamentally new ways. Let's compare how classical and quantum computers process information differently. Classical computers use bits that are either 0 or 1, while quantum computers use qubits that can be 0 and 1 simultaneously through superposition. Classical computers process information sequentially, with each bit in a definite state at any given time. Quantum computers can process multiple possibilities simultaneously through quantum superposition, enabling massive parallelism. 3 quantum properties make them powerful for artificial intelligence applications. The 3 key quantum properties are superposition, entanglement, and interference, each contributing unique capabilities to AI systems. A qubit's superposition state is represented as alpha times 0 plus beta times 1, where alpha and beta are complex probability amplitudes. Quantum entanglement creates correlations between qubits that enable coordinated parallel computations impossible on classical systems. Quantum computing enhances machine learning through several key applications. Quantum neural networks can potentially train faster by exploring solution spaces more efficiently than classical neural networks. A quantum neural network uses quantum gates to process information through layers of qubits, enabling exponentially larger state spaces. Quantum sampling can generate complex probability distributions faster, improving generative AI models. The probability of measuring state X equals the squared magnitude of the quantum state overlap, enabling efficient sampling from complex distributions. Quantum algorithms excel at optimization problems crucial for AI training. Quantum annealing can find global minima in complex optimization landscapes, helping train AI models more effectively. Grover's quantum search algorithm provides quadratic speedup over classical search, accelerating database queries and pattern matching. Quantum search achieves order square root n complexity compared to classical order n, a significant advantage for large datasets. Quantum computers process high-dimensional data more efficiently than classical systems. Quantum amplitude encoding can represent exponentially large datasets using logarithmically fewer qubits, dramatically reducing memory requirements. Using n qubits, quantum systems can encode 2 to the power n classical values through superposition states. Despite promise, quantum AI faces significant technical challenges today. Quantum systems face 3 major challenges: environmental noise, quantum decoherence, and scalability to useful problem sizes. Current quantum computers have error rates too high for most practical AI applications, requiring better error correction. Today's quantum computers have limited qubit counts, restricting the size and complexity of AI problems they can solve. The most practical near-term approach combines quantum and classical computing. Hybrid systems use classical computers for control and post-processing, while quantum processors handle specific computational bottlenecks. Classical systems manage overall algorithm flow and data preparation, while quantum accelerators handle computationally intensive subroutines. Variational quantum algorithms iterate between quantum circuits and classical optimization, combining strengths of both paradigms. The future of quantum AI holds tremendous potential as technology matures. Quantum AI capabilities are expected to grow exponentially as hardware improves and algorithms mature over the coming decades. Researchers predict quantum computers will demonstrate clear advantages for specific AI tasks within 5 to 10 years. In the long term, quantum computing could revolutionize machine learning with exponential speedups for training and inference. Let's recap how quantum computing transforms artificial intelligence. Quantum superposition and entanglement enable processing exponentially more possibilities simultaneously than classical systems. Key applications include optimization problems, probability sampling, and quantum neural network architectures. While current quantum computers face limitations, hybrid quantum classical systems are already demonstrating practical benefits. As quantum technology matures, it promises to fundamentally transform how we approach artificial intelligence and machine learning problems.